Welcome to Unacademy Computer Science. This is Umamaheswara Rao. Unacademy GATE and ESE presents Major League Compact Guaranteed Scholarship Test in Mechanical Engineering, Civil Engineering, Electrical Engineering, Electronics and Communication Engineering, Computer Science and Information Technology. Test will be conducted on 26th June at 11 a.m. Attention Unacademy GATE and ESE aspirants. Get iconic subscription at just an additional 555 rupees per month. Live classes by top educators, 8,000 plus printed and digital notes per branch, unlimited access to recorded content, priority in raise a hand and ask a doubt features. Subscribe now. Special class features, interactive live classes, polls for the learners, raise a hand option, never miss a class, lecture notes, and anytime, anywhere. Attend live classes and participate in the live chat and get your doubts cleared at all during the class, anytime, anywhere. Unacademy is conducting daily scholarship test. Grab this opportunity to win great scholarships daily. Community feature for Android that facilitates an educator and learner connect even outside the classroom. Unacademy GATE and ESE presents practice for GATE and ESE with Unacademy PYQs. Unacademy is announcing droppers batch for GATE 2023 and 24. Droppers batch for GATE 2023 and 24. Use code KUR75. Batch commences from 22nd June. Unacademy is announcing droppers batch for GATE 2024. Use code KUR75. Benefits of 1:1 live mentorship program with Unacademy GATE and ESE iconic subscription. Schedule session as per your convenience. Exam and preparation guidance. Progress report available to mentor for tracking learner activity. Unacademy is congratulating GATE 2022 top 6 rankers. Unacademy is congratulating ESE 2021 mechanical top rankers. Features of Unacademy subscriptions: top educators, doubt clearing sessions, study notes and test series, physical notes and 1:1 live mentorship program, strategy and study program, live audio interaction during open house, available for iconic subscriptions. Either for plus subscription or iconic subscription, use code KUR75. Now, PYQs on set 3. The set 1, 2, 4, 7, 8, 11, 13, 14 is a group under multiplication. Is a group under multiplication, modulo 15. The inverse of the inverse of 4 and 7 are respectively option A 3 and 13, option B 2 and 11, option C 4 and 13, option D 8 and 14. Now, option A 3 and 13, option B 2 and 11, option C 4 and 13, option D 8 and 14. Now, under multiplication modulo 15, identity element is 1. Since identity element is 1, therefore 4 multiplication modulo 15 with some element must be 1. Which element? Observe here. From the set 4, for 4, if you take 4, 4 ja 16. 16 divided by 15. 15 1 ja 15. Remainder 1. That's why 4 is the self-inverse. 4 is self-inverse. Next, we have to find inverse of 7. 7 multiplication modulo 15 with x must be 1. What is that x value? Observe here in the set. If you take 13, 7 ja 91. 91 divided by 15. 15 6 ja 90. Remainder 1. Therefore, 13 and 4 are inverses of 7 and 4. So 4 is inverse of 4. 13 is inverse of 7. So correct answer is 4 and 13. Next one. The following incomplete table of 4 element group. The following incomplete table of 4 element group, the last row of the table is multiplication E A B C, E A B C, E A B C. Here E A B C and A B C E, A B C E. Now first option C A E B, second option C B A E, third option C B E A, fourth option C E A B. CEAB. So here, given that the group is a 4 element group, order of the group is less than 6, that is a commutative group. If the group is commutative group, A transpose equal to A. Therefore, first row is EABC. Therefore, first column is EABC. Second row is ABCE, therefore second column is ABCE. Now, E is the identity element. So here E is inverse of E and A is inverse of C. If A is inverse of C, C is inverse of A. Next, C is inverse of A. Now, we can understand that identity element appears in each row at some place. Now, observe here BC. See, if the order of the group is even number, at least one element has a self inverse other than identity element. So here E is identity element, E is identity element and E is self inverse. A is inverse of C and C is inverse of A. Therefore B has a self inverse. Therefore B multiplied with B gives as E. Now BCE A. Now BCE A. Now CEA B. Now because order of the group is 4. Order of the group is 4 means order of the group is even number. Therefore at least one self inverse other than identity element. Therefore here B has a self inverse. So last row of the table is CEAB. That means last option. Last option is correct. Next problem. Let G be an abelian group. Consider the following. Consider the following relations. On G, R1, first relation, R1, for all A comma B belongs to G, A related to B, if and only if there exists G belongs to G such that A is equal to G inverse AG, G inverse BG, next R2 for all A comma B belongs to G, A related to B, if and only if A is equal to B inverse. Which of the above is or equivalence relations? Equivalence relations. Option A, only R1. Option B, only R2. Option C, both R1 and R2. Option D, none of them. Now, neither R1 nor R2. Now, here I am examining R1 is equivalence relation or not. Equivalence relation means the relation must be reflexive and symmetric transitive. Now, I am examining R1. For A comma B belongs to G, A comma B belongs to G, A R1B, if and only if there exists G belongs to G such that A is equal to G inverse BG. Now reflexive. reflexive. I am examining reflexive relation. A R1A. A R1A means A can be expressed as G inverse AG form. Because if you take G is an identity element, A is can be expressed as E inverse AE. So, for every A belongs to G, there exists an identity element E such that A is equal to E inverse AE. That's why R1 is reflexive. Next, symmetric. Suppose A is related to B. A related to B means there exists an element B such that A is equal to G inverse BG. A is equal to G inverse BG. Therefore, GA equal to BG. GA equal to BG. Now, GA G inverse equal to B. GA G inverse equal to B. B can be written as GA G inverse. That can be written as G inverse whole inverse A G inverse. It is clearly in the form of H inverse AG. H inverse AH. Not G. I have taken G inverse is H. Then H inverse AH. Therefore, for every B belongs to G, there exists an element H such that B equal to H inverse AH. That's why B is related to A. So if A is related to B, then automatically B is related to A. Therefore, R1 is symmetric. Next, transitive. Transitive. A related to B and B related to C. If A is related to B, there exists G such that A is equal to G inverse BG. If B is related to C, there exists AH such that H inverse CH. Now, A is G inverse BG and B is H inverse CH. Now, A is equal to G inverse BG. B is equal to H inverse CH. That can be written as G inverse H inverse C HG. G inverse H inverse C is nothing but HG whole inverse CHG. Therefore, A is related to C. Therefore, it is transitive. Since R1 is reflexive, symmetric and transitive. Since R1 is reflexive, symmetric and transitive. Therefore, R1 is an equivalence relation. What about R2? R2. So R1 is an equivalence relation. Now R2. What is the definition of R2? For all A comma B belongs to G, A related to B, if and only if B inverse equal to A. That means A equal to B inverse. See, if you examine reflexive relation, A related to A means A inverse equal to A. Is it possible for every element? No. Every element has, there is no self inverse. The meaning of this statement is every element has self inverse. It is not necessary. Therefore, it is not reflexive. For every element, in G, there is no self inverse. There is no self inverse. That's why R2 is not reflexive. If R2 is not reflexive, automatically you can say that R2 is not equivalence relation. Which one is equivalence relation? Only R1 is an equivalence relation. So correct answer is only R1. Only R1 is an equivalence relation. Next problem. Only R1 is an equivalence relation. Next one. Let G be a group with 15 elements. Let L be a subgroup of G. Let L be a subgroup of G. It is known that L not equal to G and size of L is at least 4, then the size of L is order of the group G is 15. L is subgroup of G, and given that order of L is not 15. Order of L is not equal to order of G because L is not equal to G. So order of L is not equal to 15, and also given that order of L is at least 4. That's why greater than or equal to 4. See, order of L is not 15 and order of L is greater than or equal to 4. By Lagrange's theorem, order of L divides order of G. Therefore, compulsory order of L is divisor of order of G. Therefore, possible values of order of L are 1 divides 15, 3 divides 15, 5 divides 15, then 15 divides 15. So here order of L is greater than or equal to 4 and order of L is not equal to 15. Order of L is greater than or equal to 4 and order of L is not 15. Therefore, the possible value of order of L is only 5. Only 5. Understood? Next one. Let G be a finite group of 84 elements. G be a finite group of 84 elements. The size of largest possible proper subgroup of G let G be a finite group of 84 elements. The size of largest possible proper subgroup of G. Order of group G is 84. L is subgroup of G, and they have given that L is proper subgroup of G. Therefore, order of L is not 84 and order of L is not 1. Order of L is not 1 and order of L is not 84. Given that L is subgroup of G, by Lagrange's theorem, order of L divides order of G. Therefore, compulsory order of L is divisor of order of G. Therefore, the possible values of order of L are 1 divides 84, 2 divides 84, 4 divides 84, 6 divides 84, 3 divides 84. 1 minute. Order of G is not, order of L is not 1 and order of L is not 84. So the remaining possible values I am writing. The possible values of order of L are 2, 3, 4, 2, 3, 4, 6, 12 and so on till 42. In the problem they have mentioned largest possible value. Therefore, the largest possible value of order of L is 42. The largest possible value of order of L is 42. Therefore, 42 is the correct answer. Next problem. Next problem. If G is a cyclic group of order, a cyclic group of order 24, then number of generators of G is, the number of generators of G is, if G is a cyclic group of order 24, the number of generators of G is, how many number of generators of group G? Observe here, given that G is a cyclic group of order 24. G is a cyclic group of order 24. Therefore, the number of the number of generators of G. The number of generators of G is given by Euler's phi function of 24. So what is Euler's phi function of 24? If you write 24 into product of primes, 24 equal to 2 into 3 into 4. Product of distinct primes, 2 3 is 6, 6 4 is 24. Now, therefore, 24 into 1 minus 1 by 2 into 1 minus 1 by 3 into 1 minus 1 by 4. That is 24 into 1 by 2. 1 minus 1 by 3 is 2 by 3. 1 minus 1 by 4 is 3 by 4. 2 to cancel, 3 3 cancel. 24 by 4. 1 minus 1 by 2 is 1 by 2, 2 by 3, 3 by 4. Now, 2 to cancel, 3 3 cancel. 24 by 4. One minute. 24 can be written as 2 12 ja, 2 6 ja, 2 3 ja. Therefore 24 equal to 2 cube into 3 power 1. That's why 24 into 1 minus 1 by 2, 1 minus 1 by 3. That is product of distinct primes. 24 into 1 by 2, 2 by 3. 3 2 is 6, 6 4 is 24, 4 2 is 8. Therefore, 8 is the answer. Number of generators are 8. Understood? You have to write product of distinct primes. So 2 cube into 3, only 2 and 3 are primes. That's why. Next. From the composition table of cyclic group, shown below, which of the choices is correct? Which of the choices is correct? Now I have to write composition table. One, 2, 3, 4. 1, 2, 3, 4. Now A, B, C, D. Here A, B, C, D. Now here A, B, C, D. Next B, A, D, C. Next C, D, B, A. C, D, B, A. Next D, C, A, B. Now option A and B are generators. A, B are generators. Option B, PC are generators. Option C, CDR generators, option D, DAR generators. Which of the choices is correct for generators? Which of the choices is correct for generators? So here all the elements are repeated in the same order in first row. Therefore, A is identity element. A is the identity element. A is the identity element. Next, from the diagram we can understand. Here we have A. Here B square equal to A. Here CD equal to A. Here DC equal to A. That means C is inverse of D and D is inverse of C. But B square equal to A. Observe. From this we can understand that A is identity element. Therefore order of A is 1. Next, B square equal to A. Therefore order of B is 2. Next, C square equal to B. C square equal to B. Therefore C power 4 equal to B square, that is equal to A. So C power 4 is equal to A. Therefore order of C is 4. Order of B is 2. Next, D power D square equal to B. Therefore D power 4 equal to B square equal to A. Therefore D power 4 equal to A. Therefore order of D is 4. Therefore order of the group is 4, order of C is 4 and order of D is 4. Therefore C and D are the generators. Therefore C and D are the generators. C and D are the generators. Understood? Next one. Now, the number of onto functions, the number of onto functions from an n element set to 2 element set E. From an n element set to 2 element set. So here cardinality of x is n, cardinality of y is 2, number of onto functions is given by number of onto functions is given by 2c0 into 2 minus 0 whole power n minus 2c1 into 2 minus 1 whole power n plus 2c2 into 2 minus 2 whole power n, that is nothing but 2c0 is 1, 2 power n minus 2c1 is 2 plus 0. So 2 power n minus 2 onto functions. So the number of onto functions from n element set to 2 element set is 2 power n minus 2. Next problem. Option A. Next problem. Next problem. Cardinality of x is x. Cardinality of y is y. Cardinality of z is z. W is x cross y. Cartesian product of x and y. E is set of all subsets of W. E is set of all subsets of W. Therefore, number of functions from set Z to E, set Z to E. Number of functions from set Z to E. Now here W is nothing but Cartesian product of x and y. Therefore, cardinality of W is equal to cardinality of x cross y. So here, what is cardinality of x cross y? Xy, because cardinality of x is x, cardinality of y is y. Therefore, cardinality of x cross y is xy. Now, E is set of all subsets of W. Set of all subsets of W means 2 power xy. So cardinality of E is 2 power xy. Cardinality of E is 2 power xy. Therefore, number of functions from Z to E is given by cardinality of E power cardinality of Z, that is 2 power xy power Z, that is 2 power xyz. Two power xyz is the answer. Understood? Next. Next problem. Let f is function from A to B, G is function from B to C, H is function from A to C, such that H is G circle F, then which of the following statement is true? Which of the following statement is true? Option A, G is onto implies H is onto. Second statement, H is onto implies F is onto. Next, see third option. H is on to implies G is on to. Last option. H is on to implies F and G are on to. F and G are on to. Now here, this is A, this is B, this is C. F is function from A to B. G is function from B to C. Therefore, G circle F is function from A to C. That is H. Now, F is function from A to B. G is function from B to C. H is function from A to C. That is G circle F. See, H is on to implies G is on to and F is 1 1. So which one is correct? H is on to means G is on to, F is 1 1. So third option is correct. H is on to implies G is on to is correct. Understood? Thank you.